Imagine you were standing on the floor of a modern biomanufacturing facility. It's Tuesday, 2:00 a.m. You're looking up at this massive, vibrating stainless steel bioreactor. And inside that 5,000-liter tank is a $10 million batch of active pharmaceutical ingredients.
A huge amount of capital on the line.
Exactly. And up in the C-suite, hundreds of miles away, some executive is looking at this pristine, centralized cloud dashboard. All the lights are green. The multi-million-dollar AI model says, hey, everything is operating at peak efficiency. But down on the floor, under the hum of the fluorescent lights, you can hear a slight rhythmic cavitation in the mixing valve.
Which means the batch is already dead.
The batch is completely dead.
Yeah,
and that state-of-the-art AI that was supposed to save it is completely blind to what's actually happening.
It's a terrifying scenario. And the crazy part is it is happening every single day. I mean, usually when we think of massive corporate failures, we expect a public spectacle, right? Like a massive product recall or a PR disaster.
Right. Stock price tumbling on the front page of the Financial Times.
Exactly. But in the landscape of modern enterprise manufacturing, the most devastating financial bleeding is entirely silent. It just quietly drains the P&L.
Welcome to today's deep dive. Because today we are pulling back the curtain on this exact phenomenon. We are looking at a very specific structural design flaw that is just draining capital across the corporate world. We're asking a pointed question. Why do flawless state-of-the-art AI models instantly die the moment they leave the pristine laboratory and hit the gritty, messy reality of the manufacturing floor?
It's an incredibly vital topic for anyone interested in, well, operations, technology, or capital allocation, because across the industry right now, we're seeing a major shift. Professionals are finally ditching the sanitized corporate press releases, and they're starting to share these raw, unvarnished accounts of where the system is actually breaking down.
And to guide us through this, we have an absolute killer stack of sources for you today. We're pulling from this wild autopsy of bioprocess data failures written by an elite, highly pragmatic systems operator, someone publishing under the persona of a quiet architect whose entire job is just building and fixing these invisible enterprise systems.
The plumbing, basically.
The literal plumbing, yeah. We're also diving into recent academic literature, including a massive review on artificial intelligence in bioprocess automation, right alongside these extensive, hard-hitting case studies detailing the actual deployment of edge AI in pharmaceutical manufacturing.
And what makes this stack so compelling to me is the absolute refusal to deal in hypotheticals. I mean, these sources are grounded in the unforgiving physics of supply chains, the stubbornness of legacy technology, and honestly, organizational psychology.
Right.
They give us the raw math on what actually happens when silicon meets steel.
Okay, let's unpack this, because before we dive into the heavy machinery, I want to give you, the listener, a conceptual framework to hold on to as we navigate this whole thing. If you're familiar with classic industrial design, you probably know the name Dieter Rams.
Oh, absolutely. A legend.
Right. And his guiding philosophy, his entire ethos, was encapsulated in just 3 words. Less, but better.
Less, but better.
It's about stripping away the non-essential, all the fluff, to find the pure, essential geometry of a problem. Like, what is actually broken here?
And that is the perfect lens for this deep dive, because right now, the enterprise AI space is just absolutely saturated with noise. I mean, it is filled with complex, glowing cloud dashboards, executives demanding this infinite stream of big data, and consultants basically selling hypercomplexity.
Yeah, selling snake oil with a UI.
Exactly. But the solution to these million-dollar batch failures isn't more complexity. It's about returning to that essential geometry. It's about fixing the physical translation of data in a way that is unobtrusive, intuitive, and mechanically sound.
Less, but better. We are stripping away the corporate fluff today. And our sources actually audit what they call the 14 hidden corporate bottlenecks sabotaging growth. We are going to hit all of them, but let's start with bottleneck number 1, which is the pristine lab training bias. And this feeds directly into the grand vision that C-suites love to sell, right? The myth of the self-driving lab.
Oh, the self-driving lab. It is the absolute holy grail for executives right now. The promise they're buying into is that you can fully automate a biomanufacturing plant from top to bottom. Like, you just give the algorithm the parameters and it just prints medicine.
And honestly, you can totally see why they want to believe it. Like, recent surveys in biotech show that these early AI pilots are incredibly promising. They're seeing faster time to target for new drugs. AI co-pilots are helping scientists synthesize compounds way faster.
Right.
So a CEO looks at that and says, amazing, the AI works perfectly in the lab. Now let's go fire the floor managers and let the algorithm run the 5,000-liter commercial plant. They expect this full near-term autonomy.
But what they actually receive is bottleneck number 2, which is fragmented pilot programs and massive catastrophic batch failures.
Ouch.
Yeah, it's brutal. And to understand why this happens, we have to look at the physics of where these AI models are actually born. So a predictive AI model for biomanufacturing is trained in a laboratory. And a lab is a highly controlled, incredibly small-scale bubble.
Great.
Data scientists are building these algorithms based on a perfect environment. The temperature is incredibly stable, the water is ultra-pure, and most importantly, the sensor data is immaculate.
Right, like if I'm a data scientist in a lab, I have, what, maybe a 5-liter glass bioreactor.
Yeah,
The sensors are completely standardized. The metadata, the actual labels on the data are perfectly clean.
exactly. The sampling frequencies are precise. It reads the pH level exactly once every 10 seconds. So the AI is learning this perfectly rhythmic, clean language, and it builds a beautiful, highly accurate predictive model based on that.
Makes sense.
Then they take that finalized algorithm, hand it over to the commercial manufacturing plant, and just assume it's plug-and-play software.
But a commercial plant is a completely different beast.
Yeah.
Like you take this pristine, highly educated AI model, you plug it into a massive 5,000-liter stainless steel tank.
Right.
I mean, the fluid dynamics alone are entirely different at that scale. The sheer stress on the cells, the aeration rates, it's just a completely different physical universe.
And that reality leads us straight to bottlenecks 3 and 4. Unstandardized plant metadata and high-frequency industrial noise.
Yeah.
I mean, the sensor layouts on a commercial tank look nothing like the lab.
Not at all.
The commercial environment is incredibly chaotic. You have heavy vibrations from nearby commercial centrifuges. You have erratic sampling frequencies where, say, a legacy sensor from 1998 might fire 50 times a second, and the metadata is just a total mess.
It's like, okay, it's like training a Formula One driver on a state-of-the-art, multi-million-dollar digital simulator, right?
Yeah.
The virtual track is flawlessly paved, the tire physics are perfectly coded, and the weather is always a sunny 72 degrees.
Yeah.
But then, on actual race day, you drop that same driver into a mud-soaked off-road rally through the jungle. You blindfold them. And to make it even worse, the dashboard inside their car is screaming check engine because the onboard computer thinks it's on a smooth track and literally cannot comprehend why the suspension is bouncing so violently. The driver just completely chokes.
That is a phenomenal way to visualize it. You just cannot force an algorithm to interpret an unmapped reality. The lab model expects this highly specific, polite dialect of data.
Yeah.
And the commercial plant is screaming at it in a completely different language at 10 times the volume.
So it panics.
Exactly. The AI isn't defective. It literally cannot read the plant floor data. So it freezes, or even worse, it makes a terribly wrong prediction based on noise.
Which brings us to the actual human fallout of this mechanical failure. Because when that $10 million batch dies, the blame game begins. And this highlights bottleneck number 7, executive software blame.
Oh, the psychological friction here is intense. Because the failure is silent, and because it's happening at this invisible translation layer between digital and physical, no one immediately grasps the root cause.
Right.
The executives, they look at their red P&L statements, they look at their broken, glowing cloud dashboards, and they immediately blame the software. They say, well, we bought a defective AI, fire the vendor.
Meanwhile, the plant managers, the gritty guys on the floor whose yearly bonuses depend on yield, they look at this failure and they blame the data scientists. They view it as pure academic arrogance. They're thinking, these PhDs built a fragile little toy in a clean room that can't survive 10 minutes in the real world.
But the tragic part is, but the C-suite and the plant managers are missing the real issue here. They are completely ignoring the frontline operational staff.
And this is where the sources get really compelling for me, focusing on bottlenecks 8 and 9, operator alarm fatigue, and the stripping of frontline agency. Let's talk about the operators for a second. Imagine you are the shift supervisor we talked about at the beginning. You are responsible for this massive facility. How does this AI failure actually affect your daily life on the floor?
To explain this, the quiet architect source draws this brilliant parallel to an intensive care unit in a hospital.
Okay, I love this analogy.
Yeah, so in an ICU, you have patients hooked up to dozens of biosensors. Historically, when centralized monitoring systems track those sensors, the chaotic real-world movements of the patient like coughing, rolling over, a nurse adjusting an IV line, Those create spikes in the data.
Sure.
The centralized system misinterprets these physical spikes and triggers false alarms.
And anyone who's spent any time in a hospital knows exactly what happens next. When a machine beeps every 4 minutes for absolutely no reason, the nursing staff learns to just tune it out. You physically have to ignore it to survive your 12-hour shift and focus on the actual human patient.
Precisely. That is alarm fatigue. And the exact same psychological adaptation happens in continuous biomanufacturing.
Wow.
When these pristine AI models are fed the chaotic high-frequency noise of the plant floor, they panic. They trigger constant anomaly alerts. The C-suite dashboard flashes red 50 times a day. And the frontline operator, who are highly skilled technicians, they look at the tank, see that it's totally fine, and realize the AI is just crying wolf.
So they just learn to ignore the alerts.
They have to, but eventually one of those alerts is real. A bioreactor actually does go out of spec. Maybe the pH level drops dangerously low, the centralized alarm goes off, but because it's the 50th alarm that day, the operator delays checking it by, say, 20 minutes.
And in continuous biomanufacturing, 20 minutes is a lifetime. The batch is ruined. The raw materials are wasted. Hundreds of engineering hours just vaporize.
This is massive capital leakage, and it's not the operator's fault. It's a systemic design failure. Which brings us to a foundational concept introduced by our sources, and it's called restorative engineering.
I really want to spend some time here because this feels like the philosophical core of our whole deep dive today. What exactly defines restorative engineering?
Restorative engineering operates on the core principle that the primary function of industrial technology must be to restore human safety, capability, dignity, and operational agency.
It's the exact antithesis of the whole replace the human with an algorithm mindset.
Completely. When executives push for full, near-term autonomy by just slapping a noisy top-down AI dashboard onto a chaotic plant floor, they are actively stripping their frontline operators of agency.
Yeah.
They are burdening these highly skilled, expensive workers with broken data pipelines and basically expecting them to act as manual filters for bad software.
They're essentially turning their elite engineers into alarm clock snoozers.
Yes, restorative engineering says, look, we must validate the invisible, undocumented labor of these frontline workers. Instead of overriding them with a fragile, panicking AI, we need to fix the physical infrastructure so they can actually trust their instruments again.
Okay, so if the AI itself isn't technically defective and the data scientists aren't incompetent and the operators are just suffering from systemic alarm fatigue, how do we actually bridge this massive disconnect? Like, how do we fix the infrastructure?
This brings us to the mechanical solution and bottleneck number 5, the cloud latency trap.
Right.
See, the industry default when an AI model fails is to just demand expensive retraining. The executives say, well, the model didn't work, send it back up to the cloud, give the data scientists another $1 million, and make them retrain it.
But that's a fool's errand. You're just retraining the model on the exact same chaotic noise.
Exactly. But there's a deeper structural issue with relying on centralized cloud analytics in a manufacturing environment in the first place. We are talking about highly regulated pharmaceutical production. Zero latency is a non-negotiable requirement.
Oh, for sure.
If a mixing valve starts cavitating or temperature spikes, you need to adjust the system in milliseconds.
You literally can't wait for a data packet to travel from a physical sensor in Ohio all the way up to a cloud server in Virginia, get processed by an algorithm, and then travel back down to the floor. Like, the round trip just takes too long.
It's way too slow. And beyond the latency, we have bottleneck number 6, IP security vulnerabilities. If you are a Pfizer or Moderna transmitting highly sensitive proprietary biological process data to a third-party cloud server, it introduces cybersecurity risks that are completely unacceptable to compliance officers.
So the cloud is too slow to save the batch, it's too vulnerable for corporate IP, and the AI sitting up in the cloud doesn't even speak the plant's language anyway.
Which is exactly why the solution is not a better algorithm in the cloud. The solution is a physical, localized translation layer right there on the factory floor.
Enter the hero of today's deep dive, the Edge AI Gateway. Let's do a Feynman compression here to make sure this is crystal clear for everyone. Our quiet architect source uses this brilliant analogy. A lab-trained AI expects to drink from a gentle, perfectly clean water fountain. But the commercial manufacturing plant hooks that AI directly up to a high-pressure industrial fire hose. The AI drowns and the system breaks.
The edge AI gateway is the physical valve bolted between the fire hose and the fountain.
It is the ultimate translator. So if I'm understanding this, it's like having a United Nations assembly where every diplomat is screaming in a completely different language,
Right.
and the edge gateway is the earpiece, providing simultaneous, perfect translation into one universal dialect for the AI. Without it, the AI is just listening to babble. But how exactly does this physical valve work? What is it mechanically doing to the fire hose?
So these local nodes, the edge gateways, are physical pieces of compute hardware. They sit right on the plant floor, physically close to the sensors. They intercept the raw chaotic data feeds before they ever reach the central AI model.
Okay,
And they perform three critical standardizations.
let's walk through them.
First, they standardize the naming conventions, the metadata. So a sensor in the pristine lab might have been cleanly labeled, say, temperature node 1.
Nice and neat.
Very neat. But the legacy sensor on the commercial tank is outputting a messy string like thermostat reactor 5 a legacy. If that hits the AI throws an error because it doesn't recognize the variable.
Obviously.
So the edge node intercepts that messy string and instantly maps it to temperature node 1.
It basically fixes the vocabulary.
Exactly. Second, it normalizes the unit outputs. The data scientists might have trained the AI using Celsius, but the plant operators might be using a legacy system outputting in Fahrenheit, or even just raw millivolt signals from a thermocouple.
All right.
The edge node mathematically converts that raw voltage into the exact Celsius format the AI expects.
And the third standardization.
This is the most crucial one. Compressing the sampling frequencies. Remember that high-frequency noise we talked about?
Yeah, the 50 times a second thing.
Right. If the lab model was trained to analyze one clean data point per minute, but the commercial sensor is firing off a chaotic spray of 50 data points per second, that noise will totally choke the model.
It's overwhelming.
So the edge node acts as a buffer. It aggregates, filters, and compresses that 50 per second noise into one perfectly clean, mathematically sound average per minute.
It literally shapes the fire hose into a gentle arc of water. The AI gets exactly what it was trained to consume.
And because this translation and processing is happening locally, at the edge of the network, right next to the machine, the latency is practically zero.
Wow.
It catches the temperature spike instantly. It alerts the human operator before the batch sours, rather than sending a neat little autopsy report 20 minutes after the fact.
Here's where it gets really interesting for me. I want you, the listener, to visualize this hardware for a second, because it completely shatters how we usually think about smart technology. Like when we hear the term AI, we've been conditioned by sci-fi and corporate marketing to picture something ethereal, right? We picture glowing blue holograms, sleek glass interfaces, floating nodes, and a pristine white server room.
Right, the cinematic illusion of artificial intelligence. But the Dieter Rams approach, what our sources actually call the active cool aesthetic, is the exact opposite of that.
Picture a heavy, unvarnished industrial edge compute module. It is a dense, matte black or brushed industrial silver box. It doesn't sit on a glass desk. It is bolted directly to heavy, vibrating stainless steel piping on a commercial bioreactor.
Out in the dirt.
Right. It's living under harsh, flickering, fluorescent factory lighting. It's connected not by invisible Wi-Fi, but by thick, heavy, black rubber cabling. There are no fancy touchscreens. There are no fake UI interfaces. There's just the subtle, rhythmic pulse of a single, dull, amber diagnostic LED indicating data transfer.
It is raw, unvarnished utility. It is designed to be completely forgotten until it's actually needed.
It is the literal embodiment of less but better. It's not trying to look smart, it's just doing the work. And that physical aesthetic reflects the reality of the industrial Internet of Things, the IoT architecture.
Exactly. To understand how this box actually functions, we really need to break down the IoT architecture into three distinct layers. This is how the physical world talks to the digital world.
Let's build the stack.
So the foundation is the perception layer, sometimes called the sensing layer. This is the raw interface with physical reality. These are the embedded devices collecting the critical variables. The thermocouples measuring heat, the optical sensors measuring particle contamination in a clean room, the pH probes inside the bioreactor.
Okay.
Without a robust perception layer, you literally have no ground truth.
Okay, so that's the eyes and ears. Then you have the network layer, which is how those eyes and ears transmit to the brain. And this addresses bottleneck number 11, bandwidth limits of traditional Wi-Fi. Because you aren't just hooking these critical sensors up to the factory's guest Wi-Fi network, right?
Absolutely not. Standard Wi-Fi is way too fragile, too power hungry, and way too insecure for a GMP good manufacturing practice environment. The network layer relies on secure, specialized industrial protocols. For example, you'll see MQTT used extensively.
What makes MQTT different from how, like, my laptop connects to the internet?
Well, MQTT stands for Message Queuing Telemetry Transport. Unlike traditional web traffic where a client is constantly asking a server, hey, do you have new data? Do you have new data?
Which drains power.
Right. MQTT uses a publish-subscribe model. The sensor only publishes a tiny packet of data when something actually changes, and the edge gateway subscribes to that specific topic. It is incredibly lightweight, requires very little bandwidth, and is highly reliable even on really flaky networks.
That makes total sense. It's just a much more efficient conversation. What else is in the network layer?
You also have LoRaWAN long-range wide area network. This is vital for facilities that span massive physical footprints like temperature-sensitive storage warehouses.
Okay.
LoRaWAN uses chirp spread spectrum technology, which allows a sensor to transmit data over several kilometers while running on a single tiny coin cell battery for years.
Years, just on a coin battery.
Years. And finally, for highly secure direct-to-tower connectivity, you'll see NB-IoT, or narrowband IoT, which operates directly on cellular bands.
Okay, so we have the perception layer gathering the data, the network layer transmitting it efficiently, and that brings us to the application layer. This is the matte black box. This is where the translated data is turned into actual decision-making. But wait, this brings up bottleneck number 10, power constraints and computational limits. If this box is just bolted to a hot pipe, it doesn't have a massive server farm cooling it down.
You've hit the major engineering hurdle. Running advanced deep learning AI at the edge of a network is violently difficult. You're dealing with severe constraints. You have limited processing power, tiny amounts of RAM, and really tight thermal limits. You can't have this box overheating next to a volatile chemical process.
So how do you take a massive multi-gigabyte neural network that was trained on a supercomputer in a lab and shove it into a low-power microcontroller bolted to a pipe?
You use model compression techniques. The sources detail 3 primary mechanical strategies for achieving this. The first, and honestly most fascinating, is quantization.
Okay, let's unpack quantization.
When an AI model is trained on a supercomputer, it typically uses very precise 32-bit floating point numbers for its calculations.
Okay.
It's doing math with numbers that have many, many decimal places. Quantization is the process of mapping those highly precise 32-bit numbers down to lower precision 8-bit integers.
So you are intentionally degrading the precision of the math. It's like taking a massive, uncompressed, raw photograph from a professional camera and saving it as a smaller JPEG file. It still looks exactly the same to the human eye, but it takes up a fraction of the memory space.
That is a perfect analogy. You shrink the mathematical footprint.
But wait, I want to push back on this a little bit. If we are in a highly regulated pharmaceutical environment, isn't intentionally degrading the precision of the data a massive risk? Like if I'm an FDA auditor, I do not want a compressed version of the truth when it comes to the temperature of a vaccine batch. Doesn't quantization compromise safety?
It's a brilliant question, and it's exactly what plant managers argue when they first encounter edge AI. But the reality of neural networks is that they are remarkably resilient to small amounts of mathematical noise.
Really?
Yeah, the data scientists run rigorous validation tests. They prove that converting from 32-bit to 8-bit might introduce, say, a 0.1% error rate in the internal mathematical weights, but it does not change the final predictive output of the model.
Oh, I see.
The AI still accurately predicts the failure. Once you validate that bounded error for the regulators, they accept it, because the trade-off is that you can now run the model in real time on the floor.
Fascinating. So you mathematically compress it. What's the second technique?
The second is pruning. A deep neural network is made up of millions of artificial neurons and connections, but not all of those connections are equally important. Pruning literally cuts out the neural connections that aren't contributing significantly to the final decision.
You streamline the architecture.
Right, removing the dead weight, which drastically speeds up the calculation time on a small chip.
You trim the fat off the algorithm. And the third strategy.
The deployment of TinyML. This is an entire subfield of machine learning dedicated specifically to running models on ultra-low power microcontrollers. Instead of needing a massive power-hungry GPU, TinyML allows these pruned, quantized models to run on specialized edge accelerators, like the ARM Cortex-M series or the Google Coral Edge TPU.
And these chips are specifically designed for this kind of rugged environment.
Yes. They can execute trillions of operations per second while drawing incredibly low power, sometimes less than 2 watts.
2 watts. A standard light bulb uses what, 60? That power efficiency must be a total game changer, especially for sensors that can't be hardwired to the grid.
It solves massive operational headaches. One of our life science case studies details a biopharmaceutical fermentation plant where their initial unoptimized edge sensors were chewing through batteries so fast that maintenance teams were constantly swapping them out.
Which causes downtime.
Exactly, localized downtime. By integrating low-power field programmable gate arrays, FPGAs, and event-driven AI models that basically sleep until they detect a significant anomaly, they extended sensor battery life by over 60%.
And beyond the battery life, shifting this compute power out of the cloud and down to the edge physically cuts the time it takes to detect a problem.
Drastically. Moving the decision-making to the edge drops anomaly detection latency by 40 to 80%.
Which circles perfectly back to restorative engineering and the human element. When you eliminate that latency and you filter out the chaotic noise, you stop the false alarms. You give the human operator a real-time trustworthy signal. You cure alarm fatigue.
Exactly. The human operator can look at the monitor and know that if the amber light is flashing, it is a real event, not just a metadata mismatch. You restore their trust in their own tools.
Okay, we've gone deep into the physics, the hardware, and the translation algorithms. We've solved the power constraints. But, hardware is not free. Bolting thousands of matte black boxes across a sprawling facility requires serious capital expenditure.
It does.
So let's audit the ROI. Let's move from the engineering schematic to the executive P&L statement. How does this gritty translation layer actually pay for itself?
Well, the data from the case studies is definitive, and it addresses bottleneck number 12, reactive maintenance downtime.
Okay, break that down.
Let's start with predictive maintenance. In traditional manufacturing, maintenance is mostly reactive. A centrifuge breaks, the line stops, and you lose millions of dollars an hour while you fix it.
Right.
Or it's preventative, meaning you swap out perfectly good, expensive parts on a strict schedule just to be safe.
Both of those are incredibly wasteful.
Yeah.
But with Edge AI,
With Edge AI, you deploy high-frequency vibration and acoustic sensors directly onto the heavy machinery, the tablet presses, the commercial centrifuges. The embedded TinyML model performs complex mathematical functions, like fast Fourier transforms, right there on the Edge chip.
on the device itself.
Right. It analyzes the acoustic signature of the motor in real time. It can detect microscopic early signs of mechanical wear, like a bearing just starting to grind, weeks before a human could ever hear it.
So it spots the failure before the machine actually breaks.
Exactly. You schedule the maintenance during planned downtime. The result: unplanned downtime is reduced by up to 30%, and overall equipment effectiveness, or OEE, jumps by 40%. That alone justifies the hardware investment.
That's massive.
Yeah.
But what about the actual product quality? How does Edge AI impact the drugs being made?
This brings us to automated quality control, specifically using embedded computer vision. On a pharmaceutical packaging line, you might have vials of medicine moving at thousands of units per minute.
A blur, basically.
Yeah, historically, checking those for defects was either done manually, which is slow and highly error-prone, or by cloud systems that just couldn't process high-res video fast enough.
I can't even imagine a cloud server trying to stream and analyze 4K video of 1,000 vials a minute without lagging.
It chokes. It just can't keep up. But with an Edge AI vision system, the camera and the processor are literally in the same box. The AI analyzes the feed instantaneously. It uses volume estimation algorithms and edge detection to look for microscopic cracks in the glass, misaligned labels, or incorrect fluid levels.
And how accurate is a quantized, pruned model doing that?
Over 99.8% accurate. Facilities implementing these edge-driven vision systems reduce their batch rejection rates by 35 to 40%.
35% less finished product thrown into the incinerator. That is pure profit recovered. And I know the sources also highlight the impact on the biological processes themselves, right?
Yes, process optimization. Biological synthesis is incredibly volatile. Traditionally, a human operator had to manually take a sample, test it, and then manually adjust the mixing speed or the oxygen flow in a bioreactor.
Which takes time.
Now, AI-driven embedded controllers create a continuous, real-time feedback loop. They dynamically adjust parameters microsecond by microsecond based on edge data. One major biotech firm reported this dynamic adjustment increased their final enzyme yield by 15%, while simultaneously cutting raw material waste by 20%.
That is the promise of AI actually realized.
Yeah.
More yield, less waste. And what about supply chain logistics? Things like the cold chain. We all learned during the pandemic how fragile vaccine temperatures are.
Cold chain monitoring is the absolute perfect use case for LoRaWAN and Edge AI. Traditional cloud alerts for temperature deviations were often delayed by connectivity drops in transport trucks or dense warehouses.
Right, cellular dead zones.
Exactly. By the time the alert came through to the dashboard, the vaccines had been too warm for too long.
They were ruined.
Totally ruined. Smart cold chain monitors with Edge AI don't wait for a cloud connection. If the temperature spikes, the Edge node immediately triggers a localized cooling adjustment or alerts the driver directly in the cab. A leading manufacturer deployed this and cut their temperature-related spoilage losses by 30%.
Okay, so the financial ROI is undeniable. Massive reductions in downtime, less rejected product, higher yield, less spoilage. But I want to talk about the elephant in the room when it comes to pharmaceutical manufacturing.
The regulators.
Exactly. Bottleneck number 13. Regulatory compliance and FDA data gaps. You cannot just bolt a new black box computer onto a drug manufacturing line without regulatory agencies bringing down the hammer.
Regulatory compliance is the most rigid, unforgiving constraint in this entire industry. We're talking about standards like FDA 21 CFR Part 11 in the US and EU GMP Annex 11 in Europe.
For the listener who hasn't had the pleasure of sitting through an FDA audit, what exactly do those regulations mandate?
So, CFR Part 11 establishes the rules for electronic records and electronic signatures. Basically, the FDA mandates that if you are using a computer to track a pharmaceutical process, that data must be absolute, immutable truth.
Ironclad.
You must adhere to ALCOA plus principles. Data must be attributable, legible, contemporaneous, original, and accurate. You need a tamper-proof audit trail that proves exactly who did what, when, and that the data was never altered.
And as we discussed earlier, streaming all of that raw, sensitive data up to a multi-tenant cloud server introduces massive cybersecurity risks. Auditors hate it because the chain of custody is too long and completely vulnerable to interception.
Precisely. If an auditor finds a gap in your data trail or a vulnerability where data could have been altered, they can shut down the entire production line. Edge AI solves this elegantly by keeping the data localized, but some case studies take it a step further. We are actually seeing plants implement localized, blockchain-secure data logging directly at the Edge node.
Wait, blockchain, not for cryptocurrency, but for compliance.
Exactly. The Edge gateway cryptographically hashes the sensor data at the exact moment it is collected, creating an immutable ledger of the batch parameters.
Oh, that's smart.
It guarantees a tamper-proof audit trail without ever exposing the sensitive intellectual property to the public internet. Facilities doing this have reported a 50% improvement in regulatory compliance auditing times because the data provenance is mathematically guaranteed.
It's mathematically guaranteed trust. Wow. If we connect this all to the bigger picture, it really forces a reckoning with how we view the future of manufacturing and automation as a whole.
It really does. The academic review from PubMed makes a very bold assertion. It explicitly states that the executive fantasy of a fully autonomous, lights-out, self-driving laboratory is entirely unrealistic in the near term.
It's a myth. The physics just won't allow it.
The biological complexity of living cells, the strict regulatory safety requirements, and the multi-scale physical differences between a lab beaker and a commercial plant mean that full autonomy is a dangerous illusion right now.
So if full autonomy is out, what is the actual trajectory here?
The future is hybrid systems. Hybrid human-machine decision matrices.
I love that phrase. Hybrid human-machine decision matrices. It recognizes that biology demands human wisdom.
It means we require sustained human oversight. Edge AI is not designed to fire the floor manager. It is designed to give that floor manager perfectly translated, zero-latency, highly accurate data so they can apply their human judgment and make the correct call. It restores their operational agency.
This is the ultimate realization of the quiet architect philosophy. When a complex system fails, the loudest voices in the room demand these expensive software overhauls. They want to fire the algorithm and build a new one. But the actual pragmatic mechanical solution is fixing the plumbing.
Right.
If you fix the physical data bridge, if you translate the fire hose into a fountain, the original software will execute exactly as designed.
You preserve your massive engineering investments by fixing the hardware translation layer. You deploy the matte black edge node, you standardize the noise, you save the batch.
But I have to push back here. We've laid out the physics, the coding, the ROI, and the regulations. It all makes perfect logical sense. But is it really that simple to implement? Just bolt a box to the pipe and the $1 million AI works. What about bottleneck number 14, the cultural shift?
The human element in the C-suite.
Right. Executives love their shiny cloud dashboards. A dashboard on a massive screen in a boardroom looks like the future. It justifies their budget. How on earth do you get a CEO to pivot their multi-million-dollar IT budget away from flashy cloud AI and convince them to invest in gritty, invisible, unglamorous floor hardware that they can't show off in a PowerPoint presentation?
That is the ultimate bottleneck, and you are entirely correct. It is not a technological failure we are fighting at that point. It's an organizational psychology failure. The C-suite has been sold a pervasive narrative by massive tech companies that cloud computing is the absolute apex of innovation. To them, hardware is archaic.
It's seen as a step backward, like we're going back to the 90s.
Exactly. So overcoming this cultural hurdle requires its own form of translation. You cannot approach the C-suite and pitch edge AI as a technical upgrade. You can't talk to them about quantizing 32-bit floating points to 8-bit integers or standardizing metadata arrays.
Their eyes will completely glaze over.
They'll tune you out.
So how do you translate it for them?
You have to reframe the hardware from an IT expense into a direct yield preservation asset. You speak to them purely in P&L terms. You tell the executive, look, we're installing a translation layer that will recover 35% of your discarded batch yields, eliminate your FDA audit anxiety, and prevent $5 million a quarter in reactive downtime.
You have to speak their specific language, just like the Edge Gateway speaks the AI's language.
Perfectly said. The human executives require a translation layer just as desperately as the algorithms do. Once they see the recovered capital on the balance sheet, that dull, matte black box suddenly becomes very glamorous to them.
So what does this all mean? Let's bring it all together. We've journeyed from the pristine, highly controlled, isolated bubble of the laboratory, where data scientists build mathematically perfect models. We've stepped out onto the chaotic, noisy, vibrating reality of the 5,000-liter commercial plant floor.
Yeah.
And we've seen exactly how the mismatch in physical data causes catastrophic million-dollar batch failures and this devastating human alarm fatigue.
And we've uncovered the vital, unglamorous role of the Edge AI Gateway. It is the unvarnished physical valve, the Dieter Rams-inspired essential geometry that translates the chaotic industrial fire hose into the clean water the AI needs to survive.
We've learned that true innovation isn't always a new, highly publicized algorithm living up in the cloud. Sometimes the most revolutionary technology is just a better, quieter valve bolted to a hot pipe on a factory floor, doing the invisible, essential work of translation.
It is the embodiment of less, but better. It is about practicing restorative engineering, validating the expertise of the frontline operators, and restoring their ability to actually trust the systems they work with every day.
And it proves that the most expensive, damaging failures in business aren't the loud, public PR disasters. They are the silent structural gaps between how we design technology in a vacuum and how the physical world actually operates.
The translation layer is where the battle is won or lost.
Which leaves you, listener, with a thought to mull over long after this deep dive ends. We've seen how our most advanced multi-million-dollar AI models completely suffocate in manufacturing, simply because they cannot interpret the messy, unstandardized data of the physical world. So look around at your own industry. Where else in our society are we blindly blaming the algorithm for our systemic failures when the real culprit is a broken, ignored translation layer between our digital dreams and our physical reality?